Okay, welcome to this lecture about the boost converter. The boost converter is the second fundamental topology about the switching mode power supply. Okay, so let me share my whiteboard. Okay, so boost converter. Let me draw the circuit of this boost converter, which is composed again by an inductor L, a diode D, then we have the switch, okay, that indeed is an NMOS switch connected in this way. Then we have at the input side the C-in capacitor in parallel to the input voltage. Same consideration we already made when we talked about the buck converter. Okay, C-in is just a simplified form of a more complex input filter for managing the electromagnetic compatibility. Okay, so this is what remains, if you want, of typically is a low pass LC filter that you can put at the input side of each converter in order to keep all the electromagnetic noise within the converter, not interfere with surrounding equipment. So basically, C-in is not essential to the operation of any converter. Okay, so even for the boost, like for the buck, C-in does not enter in any equations about the correct operation of the boost converter. It's here just to provide a filtering action at the end. Then we have also the NOT, which is the output capacitor, which is placed in parallel to the load, which is symbolized by this resistor R, across which we have the output voltage I0. I0 is the current going to this load. Remember what we said about the buck converter. The C0 output capacitance, in that case, in the buck topology, is something that is not essential to the operation of the buck, because this capacitance, C0 in the buck topology, just add an order to the low pass filter. Okay, so they have a bettering low pass filtering action. As for us, the boost converter is concerned, the capacitor C0 now is essential to the operation of the converter. Okay, because as we can see in a few moments, in a few minutes, C0 is the only way to keep the voltage V0 constant or almost constant when the diode D is off. So in that case, unlike what happened in the buck converter, now C0 is an essential part of the operation of the booster. Okay, so this C0 is part of the converter, if you want. A few words about this topology. Again, we have inductor, diode, and MOSFET as basic construction and basic building block of the converter. Okay. Now the connection between these elements is somewhat different to the respect to that we saw for the buck converter, for example. But in any case, we also have this common P node. Okay. Here we have a node that we can call in, because it's in the input side of the converter. And then we can have an output node out, okay, connected to the output node. We have an inductor current, we have a diode current, and we have a switch current, okay? Then we have also a IC not current, and then we can put the IC current with this, with this direction. Okay? And so at the input, we have also I in current, which is a DC input current. What we can say about the boost converter? Boost converter as a main characteristic is that the output voltage is always larger than the input voltage. Okay, so in that case, we can enlarge the voltage that you can apply at the input, and the voltage at the output is always large. This typically does not happen in any, for example, linear dissipative regulators. Okay, remember the regulators which you are using transistor in their active region. Okay, this is not possible for that kind of regulators. Okay? But in switch mode converters, one of the topologies, the boost, it's possible to have a larger output with respect to that of the input. The characteristic of the boost is that it is the dual topology with respect to the buck. Okay, we can say exploit this statement later in this discussion. Okay, look at the inductor at the input. Okay, remember what does it mean having an inductor in a circuit? It means that always inductors opponents to the variation of the current. Okay, changing the current flow into an inductor leads to, let's say, something which can be very dangerous. Okay, because if you interrupt the current flow into an inductor, for example, it leads to the inductor force the same current it has before the interruption. Okay, so in a certain way, dynamically, we can think about inductor as a current source. So in that way, we can say that, for example, the input capacitance as a current, which is the inductor current to which you can subtract the DC value of the inductor current. Remember the procedure we had for, say, I explained for the buck converter in order to understand which is the current flowing to input and output capacitor. Okay, we also have a current, for example, inductor current here. Then you can have this node in, and at this node you have that I in plus IC in is equal to IL. So IC in is always the difference between the current flowing to the inductor minus its average value, which is the input current, DC current. So it means that the input current flowing to the capacitor, IC in, is something which is very smooth, okay, has no, say, pulsing behavior, because it's like the current flowing in the inductor to which you, say, subtract the average value. So it's something like this, the current flowing into the input capacitor. So that means that the input capacitor has not so huge electrical stress with respect to the same input capacitance you can have in the buck converter. Remember what happens in buck converter, you have a pulsed current, okay, in which you have a certain period of time in which the current is zero, then the current is not zero in the other beyond time period. Okay, this not happens here in the boost converter. The boost converter has less stress about the input capacitor. What happened to the output capacitor? So the output capacitor again is as a current which is dictated by the Kirchhoff current law at the output node, to which you can have the IT current, then the I naught current, which is constant, and so the current flowing to the output capacitors is the diode current to which you can subtract the average value in order not to have current flowing to a capacitor without any DC value. In that situation, we will learn in a few moments that the output capacitor current is something that is pulsed. Okay? Pulse means that effectively the output capacitor has a huge electrical stress on it. So this situation is exactly the opposite situation that you learn about the buck converter. The buck converter, the input capacitor, has less electrical stress with respect to the CNOT capacitor. The boost converter, the opposite is true. Okay, so the term that dual topology for the bus with respect to the boost with respect to the buck converter, okay, begins to have some justification if you look at Lepidus. Okay? So C naught is, say, has a huge electrical stress, C in has not so huge electrical stress. In order to analyze the behavior of the buck converter, we have to devise two kinds of operation modes. One is the CCM, continuous conduction mode, and the other one is the DCM, discontinuous conduction mode, as we did for the buck converter. The procedure now we can apply to the boost. The topology is always the same. Nothing changed in the connection between the different components of the circuit. Maybe you can change the value of these components in order to operate it as in CCM or in DCM. Okay? Remember that the electrical quantity that you have to look at in order to understand if you are operating the converter in CCM or DCM is the fact that inductor current is, let's say, non-zero always in the switching period, or you have some specific interval in the switching period in which this current is null. Okay? So we can start our analysis by looking at the continuous conduction. Okay, so let's repeat our analysis that we did for the buck here for the boost converter. In order to analyze the situation, let's consider what happens in the steady state condition or cyclostationary condition, situation in which no transient are present in the circuits, or all the transients finished out. So we are just in a situation in which all variables are, say, in a steady state. We are considering all the switches, both the MOSFET and the diodes, are ideal. So when they are closed, they act as a short circuit. When they are open, they act as an open circuit. Consider all the components to be ideal. For example, the capacitance has no ESR, so equivalent series resistance. The inductor has no series resistance. Supposing also what is the small ripple approximation. The small ripple approximation states that the output voltage V naught has a ripple on it. Okay, for those who comes in the lab in the last Friday, they saw on the scope that across a DC value you have a small ripple on the output voltage. Okay, so this ripple in the output voltage is well less of the average value for small ripple approximation. So that the instantaneous quantities that you can measure at the output can be approximated by a constant value for this analysis. What does it mean? This situation means that the boost converter, when the diode is off, the capacitance C naught, which is the output capacitance, is so large that it can hold the output voltage to be constant, okay, when the diode is off. And when the diode is on, it can, let's say, recharge to the voltage VO almost instantaneously. So that means that the time constant, which is R multiplied C naught when the diode is off, is much higher than TS. Okay, so this is another condition that I put in my description, that the time constant of all the reactive elements in the circuit are very, are larger than the switching period. Okay, so then if you want the small ripple approximation in this condition that relates time constant of reactive elements to the switching period as a linked each to the other. So let's start the analysis of the boost converter in CCM, and this analysis is for cyclostationary conditions steady state. So CCM boost operation. Let's start the situation with the time instant, which is t on. So t on is the time instant in which the switch is closed. So the switch acts like a short circuit. Okay? So let's grab this specific situation. Since my components are ideal, I can say that a closed switch can be described by a short circuit. So switch is on. Here you can have the C-in capacitance cross the voltage V-in. What is the voltage across the inductor? In this situation, the voltage across the inductor is exactly V-in. Okay. Then you have here a diode which is connected this way. C0, and you have the output load R, across which you have the output voltage. So which is the voltage across the diode? Okay, this is VL, but this is VB. The voltage across the diode in this situation in which the switch is on is exactly negative V0. So we can say that VT is negative V0. So the diode is interdicted, is soft. It does not conduct any current, so we can replace it by an opposite, okay? Because my hypothesis is that you have just ideal components, so VT is minus V0 and VL is V. So the circuit is exactly this when you look at the time interval from 0 to t on, which is on is commanded to be on. So in that specific situation, you have that the input voltage, say, charges the inductance, okay? While in that specific situation, the output voltage VO is maintained to the constant DC voltage by the output capacitors. So this is in this sense, I said previously that the output capacitor C0 now for the boost configuration is essential to the operation of the circuit. Okay? Without C0 in that specific phase in which the switch is on and the diode is off, there is no way to maintain, to hold the constant voltage at that. So C0 here has that specific function to say, have this voltage to be constant. And so in the same way, we can say that during the on, that phase, the capacitor should not be discharged by R. So R multiplied C0, which is the time constant, should be well large or higher than TS, as I previously said, in order not to decrease too much the output. Okay. What about the current flowing the circuit? As you can see here, there is inductor current, and inductor current in this phase is rising up because the voltage across the inductor is constant and is the input voltage. And so this means that you have a slope of this current, which is VL divided by inductance. So the current now is increasing. This current is the same of the switch current. So the switch current in this phase is the same of the inductor current. What happens to the diode? The diode has a voltage which is more or less is constant. Remember that we are using that, say, the small ripple approximation. So we can say that it's constant because we are using this kind of approximation. So the current here is null. In that phase, the capacitor current is the same of the output current. Okay? So this is the situation that happens for the time interval between 0 and t on, in which the switch is on and the diode is off. Remember that we are talking about the CCM operation. That means that the inductor current never reaches 0. Okay, and in this framework, we can now analyze what happens during the time interval that I can call T off. So the time interval between T on and the end of the switching period. This time interval, which is also called T off, the switch is commanded by the gate driver to be off. So to be off means an open circuit. Okay. So let me draw my circuit in order to understand what happened. Now the switch is open. This is the input capacitors across the input voltage. So what does it mean? The inductor current is always positive. So that means that before the on, so before opening the switch, I have a positive current flowing to the inductor. This means that you have a magnetic field that is established in the across the inductor. When you open the switch, okay, and this inductor current cannot be, say, reduced to 0 instantaneously. The inductor forces the current that flows through it to remain the same as before the opening of the switch. This is the, say, classical operation of an inductor to maintain constant the current flowing through it. Since this current cannot flow through the switch, which now is open, we search for another, say, path to which this current can flow. So that means that the other flow path it found is across the diode. Okay, the diode is the anode, is the cathode of the diode, can have current flow through it only if it is on. So the diode becomes on in order to make the current for the inductor to continue to flow. Okay? Exactly what happens in the buck converter. R and CO and V naught completes our circuit. Now the situation is that the switch is off and the diode is on. The diode is forced to be on to conduct current due to the presence of the inductor that forces current to not change when I change the status of the switch. So we can say that the current through the diode is the same as the current through the inductor. Current through the switch is null. In that specific phase, now we have that the input source, the charge, capacitance, and also the load in this way. Okay, you can take power flow which reaches exactly there. And make possible, for example, for the C0 capacitors to be recharged. So in that specific situation, which is the voltage across the inductor, the voltage VL across the inductor, you can make the Kirchhoff voltage law. For example, you can see that here you have V in, and then you have V naught here. So VL is simply V in minus V naught, which we can take constant due to the small approximation. Remember that V naught is negative. So sorry, V naught is larger than V in. Okay, so this means that in that case VL is negative. Okay, but this is correct because the inductor, in order to force the same current flowing, the same way it did for the situation which is closed, it actually reverts the voltage across it in order to maintain that current flowing. So it's not a problem. Okay, the same happens for the buck converter, which is the voltage across the diode. The voltage across the diode, of course, is null, and this is an approximation because we have also in that situation the gamma, the forward voltage across the diode, which now is neglected. Okay. What happens so for the current flow into the inductor? Since VL is negative due to the fact that VO is larger than in, the current across the inductor is, let's say, decreasing down to lower value, okay, because the slope is negative. It's VL over L, which is now is that. Okay, so now ID is IL, I switch is null. In the same way, in the previous situation, we have that I switch is IL and AD is. So let's derive the conversion ratio, so the ratio between the output voltage and the input voltage for the boost operated in continuous conduction mode. So let's derive the M-CCM ratio. Okay, so the PO or P naught over V in continuous conduction mode operation. We can carry out the same procedure that we already had for the buck converter. Okay, so for example, we can look to the voltage across the inductor. Ts is the switching period. We can have, for example, T on here. So in that time interval 0 T on, the voltage, so the switch is on, diode is off. So what happens to the voltage VL? The voltage VL is exactly what we have here. The voltage VL is V. Okay? Across the inductor, there is that voltage V in. We have here V in. What happens in the time interval from T on to Ts that I call T off? The switch is off. The diode is on. The voltage across this inductor here is V in minus V naught, which is negative. Like this. Then the cycle repeats itself. Here you have V in minus V naught. Okay. Remember that in a cyclostationary condition, holds the voltage per second law for inductors. That means that the DC voltage across inductors in steady state condition is always null. So you can say that PL average value is null in cyclostationary condition. So what does it mean? It means that this area has the same value of the negative area. A plus is the same of A minus, if you want. So which is A plus? A plus is V in multiplied T on, or if you want to describe this graph, you want to rescale the horizontal axis by, for example, this is T. If you want to rescale by Ts, then T on is the same of D, and Ts is the same of 1. Okay, just a constant factor by which I can rescale the vertical result. So I can say that V on multiply T is equal to what? V in minus V naught, which is negative, so we have to put right here, multiply 1 minus V. So from this basic equation that comes out from the voltage per second balance, so the fact that no DC value across the inductor is admissive in steady state condition, we can say that V on, sorry, V naught over V in is MCCM is 1 over 1 minus. Solving this expression for the ratio V naught over V, you can get 1 over 1 minus V. Okay? Remember that in the back, the conversion ratio MCCM is like D. Now is 1 over 1 minus D. And this is correct because D ranges from, say, 0 to 1. So that means that 1 over 1 minus D is always greater than 1. Okay, so that means that the output voltage V naught is always larger than V in. Okay? So this is the conversion ratio for the bar, for the boost in CCM. Try to plot this conversion ratio versus D. Here ranges from 0 to 1. Okay? So here you have M, CCM, which is 1 over 1 minus. When you have D 0, then you can have 1. Okay? What happens when D is 1? When D is 1, if you look at this conversion ratio expression, you can get infinite value. Something like this. Is it possible that, what does it mean, M, which is infinite? M infinite will be, means that MCCM going to infinite means that VO not goes to infinite. So I can reach infinite value of the output voltage. Look at the situation in which D is equal to 1. D equal to 1 means that for the entire duration of the switching period, yes, the switch is always on. So in that specific situation, which D is 1, we have to face these circuits. Switch is on, so 0 to 1, always. And so the D equal to 1 means that also the diode is off. Okay, D is the duty cycle here, and D is the name of the diode. Okay. The diode here is off. So in that specific situation, my analysis, my equation says that the output voltage goes to infinite. But this is a nonsense, because in that situation, the output voltage is maintained to a specific value by the charge inside this capacitor. Okay? But even if you get a very large value of this capacitor, if you take D equal to 1 forever, there is no possibility that the output voltage goes to infinite. I think that the best situation is to be much more understandable if I said that the output voltage goes to 0 at the end of the time. Okay? So this is actually what happens. This is not a realistic situation, having infinite, so output voltage infinite for D equal to 1. Why we get this result? We get this result because we are using a description in which all the components in the boost converter are ideal components. Okay? But in practice, uh, this never happened in practical circuits. Okay? Let me show just a very easy way to demonstrate that when you get D equal to 1, the conversion ratio of the boost converter is the same, goes to 0 and not to infinite. Like, let's say, intuitively we can understand by looking at this. So in order to understand what happens here, let me show a way to describe the operation, the large signal operation of a converter by using transformer, very special transformer. So this is ideal DC-DC. So it's a box inside which we have inductors, capacitors, switches, diodes, etc. So we have the input voltage, the input current here, I naught, and the naught output voltage of the output voltage. In lossless circuits, always you have that the input power is the same as the output power. And the input power is given by the multiplication, the product of input voltage and input current. While the P naught output power is given by V naught multiplied by naught. Remember that the M conversion ratio is V naught over V in. But using this simple lossless equation, then we can get that V naught over V in is also the same of I V in over I naught. But look now at these two equations that can be derived from this one. We can have that we have V naught is the same of M conversion ratio multiplying V in, or I in, which is M multiplying I naught. These two expressions are the same equation that you can have by using a transformer. If you have a transformer, okay, and supposing that the conversion ratio of this transformer is exactly the conversion ratio M, okay, and in this transformer you have V in applied at the left port. V in is the current that enters the port. I naught, which is the current exiting from the secondary side of the transformer, and V naught is the secondary voltage, okay, then you can have the same expression. So these two relationships here describe a transformer having a conversion ratio or a turn ratio, which is M, equal to the conversion ratio of the converter. And this transformer is just a mathematical description of that. It's not a real transformer that you, so I want to avoid any confusion. It's not that you can use a transformer in place of the converter, okay, having this conversion ratio. For several reasons. The first one is that the conversion ratio, the turn ratio of the transformer M, depends on D. So it's not fixed. So you have to change depending on D. Okay, in that case, for example, M is 1 over 1 minus D. So it depends on the side. Okay. So it's a transformer very special which has a variable turn ratio. The second one is that V in is a DC quantity. I in is a DC quantity. V naught is a DC quantity, okay, if you consider this more ripple approximation. I naught a DC quantity. So this is a transformer that converts DC electrical quantity, which is just a mathematical abstraction. It's not exist in practice. Okay, you cannot build a transformer that converts, say, DC quantity. Okay, transformer always works with alternating waveform, IC waveform. So for that reason, this is a mathematical, say, abstraction of this kind of relationship, and we can put and some books put this sign here just to indicate that this is a special transformer, is an ideal transformer, is something that does not exist in practice because it transforms DC. Okay, this flat signs here means that an abstraction to say converts DC font. But we can use this kind of description in several situations. For example, here you can use this description to understand what happens in practical circuits in the situation in which the duty cycle is 1, to get a more practical card, because this is just an ideal card. Okay, so let me show what happens, for example, for the boost CM. The boost CM is something that we can describe in this way. L, then you can have a switch, which is a MOSFET, for example. Then you can have a diode here. Let me draw the essential CNOT capacitance. Circuits. Let's do not consider the input capacitance. This is not essential to the operation. Okay, so this description is not essential to have seen. So inside this box there is the ideal boost. Okay, here you have the in, then you have the in, you have I naught, and you have the out. Okay, so this red dashed box here is exactly what is inside here. Okay, so we can use at these two ports, input ports, output ports, a description in terms of this equivalent DC ideal transform. Okay, for example, we want to investigate the effect of a equivalent series resistance of the inductor. Remember that real inductor always has in series a parasitic resistance. Okay, so ideal inductor are like this. Real inductor are better described by something like this. Okay, this equivalent series resistance, which is the representation of the losses that you can have in the copper, in the metallic material that you are using for, say, the wire by which the inductor is composed, is also called RL. Okay, RL is something that I can use here. In the slide, I use R in. Okay, is the series equivalent resistance. Okay, for the inductor of a real practical inductor. So let me insert here this RL inductor. Okay. And so if I use this RL inductor, so I'm evaluating what happens if I consider an inductor R not ideal, but a practical inductor, so I insert this. I can use the equivalent transformer model. Equivalent transformer model is something like this. I have this R inductor, then I have the ideal boost, and I have V naught, I naught, I have V in, I have V in. Okay? So, in place of this ideal boost, I can put the ideal equivalent transform. Journal ratio, which is equal to M. And now I have to put equivalence resistance here. And I have here I naught. And then I have, for example, load here. And I have, okay, supposing that I have a resistor as a load here. In which M is 1 over 1. Okay, so let me derive the expression of V naught in this circuit, in which you have a resistor, RL, and an ideal transform that transforms the DC. Let me draw here just for sake of my circuit. R V naught inductance, input voltage, input current, output current. Okay, and this is an ideal transform. So let me look at the output side, and looking at the secondary side of this transformer, evaluate which is the equivalent Thevenin circuits from, let's say, A B node. In order to do that, we have to find out a series representation of an equivalent voltage and equivalent resistance. Okay? So in that situation, which you have a transformer, it means that you have to take this resistor and put on the secondary side, and you should know that in that specific situation, this means that RL should be multiplied by the turn ratio square value, while the voltage, equivalent Thevenin voltage, is simply V multiplied the turn ratio. Okay? So they are the same terminals, AB, and this is the equivalent Thevenin. Okay? Remember that M is 1 over 1 minus V for the boost CCM. So V naught is V in multiplied M multiplied R plus RL M squared. So we can say that it's V in, replace M with 1 minus V. Let me divide numerator denominator by R. So I have RL over R, 1 over 1 minus V. So V naught over V in, we can say with inductor resistance in series, of the situation in which we are evaluating the copper losses inductor, which is MCCM, is 1 over 1 minus V, and this is the MCCM for RL0. So it is the ideal conversion ratio without any losses. So ideal component, multiplied 1 over 1 plus RL over R 1 over 1 minus 3. So we can say that this is the real conversion ratio for the boost in CCM operating mode when we consider that inductor copper losses is the same of the ideal conversion ratio without any RL resistance multiplied by a terms, which is this one, which has the significance of an error term. Okay? This error term depends on RL, the load resistance R, and depends on the duty cycle. Let me now replot the conversion ratio versus D 0 to 1 of and comparing it with the ideal situation, which is this one. This is the ideal one. Okay, and a more practical situation, for example, the one that I described in this, with RL inductor copper losses taken into account. What happens if if D is 0? If D is 0, if you put D 0 here, you can say that also here you have something that is 1 plus RL over R. Okay. This expression is more or less equal to 1, since typically the copper losses are well less than load. Okay, so we can say that 0, then you can have something which is more or less the same of the ideal MCC. What happens when D is equal to 1? When D is equal to 1, then it depends. Look at the situation in which you have to compare RL with R1 minus D. Okay. If RL is, say, well less than R minus D, then it means that the curve is more or less typically, you can say, is something like this. Okay, so it's very similar to the ideal one. Okay, since this term is almost null, this term here prevails. So this happens for which is less. However, when RL is increasing, so we are for the duty cycle, for which, for example, for large duty cycle, in which 1 minus D is very small, so higher range of duty cycle, this inequality is not always true, and so that means that in this situation, this part here takes a certain, say, effect on the equation. In that situation, if you put D equal to 1 in that specific situation, make the computation, you can say that you have something like this. So it goes to 0. If this one goes to 0, then you can have something like this, and this is for RL over R, which is so if RL is very small, then you can have a behavior which is quite similar to that of the ideal case for, say, a higher range of the duty cycle. If RL over R is less, then it happens that for a certain high level range of D, say up to a certain point on, then you can have a reduction of the output voltage with respect to that you can have in the TS situation. Okay? So that's exactly the real practical situation. Practical situation is always MCCM, so D not over D, that is 0 here, sorry, 1 here, and then goes to 0 for duty cycle, which is 41. Typically, the peak value of this curve is, I don't know, between 0.65, 0.8, we could say 0.8 of the duty cycle, you can have the maximum for typical copper losses. Okay? If you have less copper losses, so if RL is well lower than 1 minus D square R, then you can have this maximum duty cycle, which is watching the. So anyway, a more practical, more real situation is the one I depicted here, in which the duty cycle for a bus, for a boost situation, cannot reach 1, because in that situation the output voltage can decrease even to values that are lower than 1, so no more a boost, for, say, the higher range of duty cycle operation. So typically, when you have a duty cycle boost converting DCM, you have always a maximum duty cycle to which you can operate it, which depends on the parasitic. For example, the copper losses you can have in this. Okay, so take into account this fact, because the boost operation is not, say, for fully variation of the duty cycle from 0 to 1, but you have some specific limitation due to the parasitic. Okay? So this is the real conversion ratio curve that we obtained by using this powerful description, which uses this equivalent transformer, a very special transformer which has a Turing ratio which is variable with the duty cycle, and that can convert the DC electrical flow. Remember that for each of our operating state of converter, we have to define some specific, say, quantities, small signal quantities, that are the audio susceptibility for the variation of the output voltage for the variation of the input voltage. And this is always, for any kind of converter, always equal to the conversion ratio. In that situation, CCM is 1 minus. Then we have also the small signal output resistance. Is the delta V naught over delta I naught, and this is 0, okay, because V naught only depends on V in multiplied 1 minus V. So there is no presence of the output resistance in this expression. So if you take the derivative versus delta I naught, you can get 0. So that means that output voltage is, let's say, our output port has no output resistance, so the push CCM operates like a very good regulator of the output voltage, okay? Because changing the output current, it cannot change the output voltage, okay? Which is something very good. Then we have also another parameter which is called the gain, delta V naught over delta V. So how change the output voltage for small variation of the duty cycle? It means that we have delta D over V in 1 minus V. This is the derivative that we take. And this is V in 1 minus v squared value. So it depends on the duty cycle. When the duty cycle increases, okay, so the duty cycle is getting higher, the gain of the overall system decreases. Remember that also I have that VO over V, V naught over V is 1 minus 1 minus V. So I can say that V naught over V in square value is 1 minus V square value. Okay. So I can use these expression here. I can replace this numerator. So I can say that V in multiplied VO V naught square V in square. So an alternative way to represent it is in this way, V naught square over V is the gain. So V naught is constant, so it changes with the input voltage. Increasing the input voltage, it means that the gain decreases. So this is what happened for our boost CM operation. So we are just describing the happens in this as operating this boost in CCM. Let's have a look on the waveform of the current flowing in through the components in order to just evaluate some critical condition in order to design the boost in CCM and PCM, so the same operation that we already have for the boost converter. Okay? So for example, let's have a look on the inductor current. Inductor current in CCM has the classical behavior. Let me rescale the axis first. Yes, so we have 1 and 2 cycles. So what happens during T on? So from 0 to D. During T on, as I said before, in one of my previous plots, let me check here. Here, the switch is on, the diode is off, and so the voltage across the inductor is the same of the voltage at the input. The in, VL is equal to V. So that means that the current is increasing with a slope which is V in over R. What happens during T off? During T off, the voltage across the inductor is V in minus V naught. So it is negative because V naught is larger than V in, and so the current is decreasing. So let me plot the current according to these slopes that I just commented on. Let me show that this leads to this waveform. We are in CCM, so the no inductor current is 0. So we can start from a non-zero current, which is the minimum current here, to reach a maximum current at the end of this interval. The slope is positive and it is V in over I. What happens at the second part during T off? So when the switch is off and the value is on, then we have a descending current. The final value should be the same of the start value of the current because we are in cyclostationary condition, steady state condition, so there is no transient. So this always happens, and the slope here is V in minus V naught over L, okay, which is negative, okay, which is the average value of this current. The average value, IL bar, or simply IL in capital letters, but the inductor is in the input side of the boost converter, okay? So that means that the average current flowing here is the current flowing in the input source, is IN, because no DC current can flow through the Cin capacitor. Okay, so this current is always IN. So this value here is IN. And the average value is given by P maximum plus P minimum divided by G. Okay? Remember that V naught multiplied I naught is equal to V in multiplied I in, due to that situation that I'm designated here. So lossless circuit, V in is the same as V naught to the power. And so I said that I in is I naught multiplied 1 over 1 minus 2. And so I have average value, which is I in, is I naught over 1. I naught is V naught over R 1 over 1. So this is the average value that you can have here in the inductor. Okay. Remember that we are always interested in the peak-to-peak variation of this current, of conductor current, which is called the conductor current ripple, delta IL. Okay? So delta IL is I max minus I minimum. How can we derive this expression? Oh, you know that we have here a certain slope, which is P over L, and this happens during the T-on period. Okay, so if you know the slope and we know the period in which the slope falls, then we can get delta L. So delta L is simply given by P in over L, which is the slope, multiply D, and then multiply Ts. Okay, because Ts is T-on. Is V in over L dFs. Or if you want, you can compute the same ripple looking at the T-off period, okay, in which you have this slope, which is negative, okay, and it occurs during the time interval from T-on to Ts. Same way here, so it's V naught minus V in to get its positive, L 1 minus D divided by. Okay, so V naught, we can expand this expression because V naught is 1 minus V in over V naught multiplies 1 minus D over LFS, but V naught over V in is 1 over 1 minus D, and so V in over V naught, which is the reciprocal, is 1 minus D, so you can use this one here, and then you can get V naught D 1 minus D per LFS. Okay? You can use this one, which is derived during T-on, or this one, which is derived during T-off. They are absolutely the same. So from delta IL and the average value indicated here, you can get the maximum value. I max is the average value plus delta IL divided by 2. I minimum is average value minus half the value of the ripple. So it's V naught over R 1 by 1 minus D plus, let me choose the second one, 1 minus D, D 2 times FS. and V minimum is 1 minus V plus, sorry, minus V naught 1 minus V over QL. Okay, so from this inductor current, we were able to derive the maximum value, the minimum value, the average value, and also the ripple value. Okay, so we can start tomorrow from these equations about the inductor current in order to understand how to choose the inductance L in order to operate the buck converter in CCM or to operate it in DCM. Okay. I hope that all that I said was clear. Mondin, Nicolò, are there any problems to hear me? Costa Giulio, to demonstrate, then I had in the beginning. Okay, I'm sorry, but I have no, I didn't look to the chat, so I cannot say react immediately. Okay, but the feedback is not so fast. That's Costa Giulio, to demonstrate that MCM cannot go to infinity, can I say that when the diode is soft, the open circuit is the CO closed with a certain initial DO condition overload, and so that with the yes, you can also say that there is when you hold the situation in which you can have always a diode off. Okay, of course there is a point which you have no more energy transfer. Okay, from the input to the output. So that means that at a certain point the output voltage cannot go to infinity. Output voltage is let's say must go to zero from the situation. Okay? Of course, this can, as I can see in my demonstration, I try to demonstrate that this not only happens when D is equal to 1, but even when D is very large, depending on the ratio between RL over R. Okay, for example, for duty cycle higher than 0.8, it's very difficult to have an increasing M as in a DR curve. Okay, not only to equal. Equal one you can have, you're right. Other questions? Yes, okay, the proof with the transformer also for other values of D, but exactly. As you can, if you compare the practical curve with RL different from zero, you can see that there is a interval of duty cycle in the higher range of value for the duty cycle, for example, higher than 0.8, depending on the RL, in which there is a very huge difference between the ideal curve and the real practical one. Okay? M is lower, very lower than the ideal case. Okay. With D equal to 1 is quite clear that you cannot have any energy transfer for the input voltage and output voltage because there is no connection between the input and the output. So it should be clear then. Okay, if you have no other questions, I can say that we can see each other tomorrow morning starting from 8:30. Okay, continuing this discussion. Thank you very much. See you tomorrow.